Hello, everyone, and a very good morning to all of you. Distinguished delegates, speakers, and participants from SAARC member states and other regions around the globe. Ladies and gentlemen, I'm very thankful to all of you for joining us in this series of SAARC Webinars 2025. My name is Hassan Javed. I'm a research fellow, Renewable Energy at SAARC Center, Islamabad, Pakistan. I shall be moderating today's webinar, the aim of which is to discuss the challenges of increasing quantum of renewable energy in the electricity mix of SAARC member states. We have engaged regional experts who shall discuss and provide solutions with practical examples for keeping intact the stability and reliability of the electricity grid. Dear participants, you have the opportunity to ask questions during the webinar. You may send in your questions in the time during the presentation, and collect these and address them during the question answer session of each webinar, of each presentation. With this, now I request Mr. Abdul Rashid Jokio, who is the Director of SAARC Energy Center, for his opening. Over to you, sir.
Thank you, Hassan. Dear participants, speakers of the webinar, good morning. My name is Abdul Rashid Jokio. I am Director, SAARC Energy Center. It is my great pleasure to welcome you all this SAARC webinar on grid practices advancing renewables-based electrification. As a technical arm of the SAARC Secretariat, SAARC Energy Center has undertaken various interventions to promote cross-border energy trade, foster renewable energy development, promote rural electrification, enhance energy efficiency, and build capacity of the energy professionals of the South represents nearly 25% of the world's population. And energy security and reliability is an important agenda for the prosperity of the South Asian region. Our goal is to foster dialogue, share knowledge, identify practical steps we can take to build more robust, resilient, and sustainable energy system. Ladies and gentlemen, as we see significant growth in renewable energy from solar to wind power across our region, the potential to decarbonize our economies and enhance energy security is immense. However, this rapid growth brings significant challenges integrating integrating variable renewable energy sources into existing ones. Often aging power grid systems require careful planning and advanced technologies to maintain stability and reliability. Issues like grid stability, instability, power quality, and the need for flexible system operation become paramount when grid is dealing with fluctuating renewable generation. Today, we will explore pioneering solutions and best practices that are already enhancing grid performances and enabling deeper integration of the renewables without necessarily building new massive infrastructure. Dear participants, we are privileged to have very prominent regional experts, Engineer Mohammad Zakaria and Mr. Akam Ilyas, who have joined us today in this webinar from Pakistan. We hope that their insights and expertise will enrich our understanding of sustainable electricity grids for a renewable powered future. I thank you all for joining this webinar. I expect this event to be an interactive session, so please feel free to join the discussion and express your valuable opinions. I hope this session provides valuable insights and sparks productive discussion. With these words, I declare the session open. Wish you all very comfortable learning and knowledge sharing experience. I request Mr. S. and Javed to take the agenda further. Thank you.
Thank you very much, sir. So now I will introduce our first participant, first expert, Mr. Arka Makeel, who has 15 years of professional experience in power transmission and distribution sector. He has successfully contributed hands-on work, prepared several projects related to power system expansion being financed by international financing institutions. As a certified electricity market professional and an Erasmus Mundus fellow, coupled, he has developed distinguished expertise to tackle the problems related to integration and evacuation of clean energy to power networks, carbon emission reduction, and access to electricity. So we would like to ask Mr. Alsam Akeem to start his presentation. Over to you.
Thank you, Hassan, for the introduction, and thank you, Director SAARC Energy Center, for giving me this opportunity to present today. So, as Mr. Hassan has already introduced myself, so I'm working in Lahore Electric Supply Company for 15 years now, And for this today's session is very interesting in context of how we can keep moving forward with having more renewable energy in the power grid and without compromising the grid stability and grid reliability. Let me share my screen and then we can just start. So I hope my screen is visible to everyone. So just to begin with, we will just have a brief overview of the current renewable energy uptake in the Southeast Asia, and what are the current stats and renewable energy numbers, how much quantum has already been added in different countries in off-grid or even in grid integrated model. So we will just begin with that, and then we will move forward from there. The peculiar case of Pakistan and how like 5 years ago we did not have a significant footprint in the renewable energy sector, primarily the solar and wind energy, and now we are one of the leading solar energy producing countries in the world. So to begin with, we have right now India is leading the way in Southeast Asia with 51.5 gigawatt of wind energy operational right now in the Indian power grid, and with Pakistan,
If I may interject, your slides are not visible. Can you share the screen?
Just a minute.
Previously, you had shared your screen, but now it's not there. Yes.
Is it visible now?
Yes. Yes. Now it's.
Okay,
no, again we lost you. I think you may not do it the full screen version. Before it was visible.
Is it okay now?
We cannot see your screen.
Okay.
Yes, now it's visible, but I think when you do it on the full screen version, then it just gets away. I think you can continue.
Okay, so I will continue from here. Yes, so we can see that India is leading the way with the highest number of installed wind capacity, wind power generation capacity in the power grid. With Pakistan, we just have around 2 gigawatt of renewable energy coming from wind power plants, and Sri Lanka has a very small number, and Bangladesh obviously is just starting to pick up the pace and to install more renewable into their power system. So for the solar, basically for the solar power systems, were in India obviously leading the way with 14 plus gigawatt of utility scale PV systems already installed and up and running in the country, and going forward, their targets are ambitious with 39 plus gigawatt to be added in the next in the coming year. But Pakistan, if we can see that we have only 500 plus megawatt of utility scale big solar power plants in the system, and we on top of that we have 7,000 megawatts or 7 gigawatt of rooftop distributed energy resources, and this is a peculiar example and very interesting case to which we will look forward going into the presentation. And this has generated 25% of our national electricity requirement just recently. Bangladesh obviously has 2,000 megawatts or 2 gigawatt of installed solar PV system, and the target is 3 gigawatt in this coming year or in ongoing year. But Sri Lanka is also a very interesting case where they have 1.7 gigawatt of rooftop solar already installed, and the pace at which it has installed is significant. It's more than 250% rise in just one and a half year, and it will definitely cross 2 gigawatt milestone in 2025. So if we just see the installed capacity of the whole power system and versus the Chinese PV import in the system for each country up till the year 2024. So Pakistan leading the way with 46 gigawatt of installed power generation capacity in the country, and we have imported 36 gigawatt of solar PV systems up till the year 2024. So this is huge, which is almost 78% of the installed base of the country. India obviously has a very big base with 472 gigawatts of installed capacity, and they have imported 87 gigawatt till the year 2024. So that is not a big number in terms of percentage, just 18% of their total installed base. Bangladesh obviously has 26,000 megawatts of power generation facilities in the country, and their import number is 2 gigawatts. So it's also less than 10% of the total installed base in the country. So Pakistan renewable energy surge is pretty outstanding, and 500 megawatt of utility scale systems are already up and running, and we have 7 plus gigawatt of rooftop solar installations already in the country. This number is pretty big, and this is all being installed at the low voltage and medium voltage level in the power grid. So primarily, it is integrated into the distribution grid of the country. With wind energy, it is 1.9 gigawatt, as I already explained. So this is constant, and this is no new projects right now are in the pipeline which are being constructed. So this quantum or this segment of the rooftop solar PV system is gaining momentum and being installed exponentially in the country. And because of this huge quantum, the solar energy has generated more than 25% of the energy needs of the country in 2025, which is huge. Just if we see in the last fiscal year 2024, the top 10 destinations of Chinese PV export. So Pakistan was nowhere in the top 10 in just like 3-4 years ago. But just in 2024, Pakistan became the fourth largest export destination of solar PV imports in the country, in the region, basically. So Pakistan obviously has imported around $2.1 billion worth solar panels in the country, primarily because China has oversupply of solar PV systems in the country, and they export the international markets to export their surplus production capacities. And Pakistan favored this import and all these things because they exempted all these solar PV systems from any sort of import duties or regulatory tariffs or anything. While on the other hand, if we compare with Indian market, so India obviously imposed some certain tariffs, import duties on that. So that is why in Pakistan it became more and more economical or cheaper to install solar PV systems. And obviously one of the other drivers for solar PV import uptake was the rising electricity cost from the national grid. So if we just see the trend, how it has evolved, the Pakistani context from starting in fiscal year 2021, and then going forward, if we see it was just 1.5 megawatts or 1.5 gigawatts of total solar PV imports in 2021, and it was very steady growth in 2022 and 2023, where the things started to pick up. So there we have more than 4 gigawatt being imported in the country. Then we have in fiscal year 2024, as I already explained, we have 16 gigawatts of solar PV system imported in the country. And then again, the same momentum is continued, and in fiscal year 2025, we have almost 15 gigawatts imported in the country just in three quarters. So this is staggering, and this trend is rising exponentially. So this will definitely create problems in terms of grid stability and reliability. So if we just see how Pakistani market has evolved over the years, in 2029, the national share of electricity generation from the solar PV systems was just under 2%. If we can just see the blue line here, so it was just 2.5% of the national electricity generation, monthly generation of electricity in the country. And because of the massive import and installations of solar PV systems, now it has gone up to over 25% just in the summers of 2025, which is huge. And that is outstanding, and that will definitely has started creating challenges for the power system reliability and continuous power system operation. So with these numbers in Pakistan, so what are the great challenges with higher renewable energy penetration in the country? So whenever we have solar PV systems, we already know that wind and solar PV systems are weather dependent. So their output is obviously intermittent and continuously varying in nature. So when we have this continuous variation, it is very difficult for the power system operator or the national power control center of any country to maintain stability in the network. So they definitely have to keep on changing output from different dispatchable generators to keep the system stability stable and to keep the frequency at the constant 50 hertz or 60 hertz level, whichever is the national standard. And obviously, at the same time, the demand for electricity also varies, so it is not a constant parameter. So both these parameters coupled with create the instability in the network. Similarly, when we have more and more inverter-based generation system in the power network, so we will have very few. Our overall system inertia is reduced because we do not have more generators, synchronous generators supplying electricity to the power pool. So which obviously creates frequency instability as well as the voltage stability issues in the dynamic state. So we definitely needs more fast frequency response systems in the power system. So when we have these sort of issues, so the need for energy storage systems where we can have batteries as energy storage systems or pump hydro to produce in the hours of peak production from renewable energy, we can store this surplus of energy into the battery energy storage system, or we can use the same to fill out the reservoirs in terms in context of pumped hydro storage systems. And obviously, when we have this huge penetration of renewable energy in the system, then we definitely need more spinning reserves to compensate for the variation in the generation outputs and the intermittent nature of the solar and wind energy system. So we have to have hot reserves in the system and spinning reserves for primarily being provided by thermal power generation stations. And obviously, the need for flexible generation where we have gas turbines or hydro turbines where you can, quickly ramp up or ramp down the output to balance the energy demand and supply and to maintain the frequency and grid stability at a constant level. So with more renewable energy being added in the system, so we definitely have to overloading or congestion in the transmission system where we will definitely need to build out more transmission infrastructure that definitely needs a lot of capital as well as a lot of time required. And obviously, in certain areas, that's also not an easy thing because the right-of-way issues and challenges associated with constructing high-voltage transmission lines. With grid congestion, that is also a bottleneck where we definitely have to, in certain number of hours when we have or surplus generation from renewable energy sources, we might have to curtail this, or we might have to, curtail or the output from wind power plants or even solar power plants to when we are not able to offtake this into the national grid when there is no demand or when there is transmission bottleneck. Similarly, when all these systems are coupled, then the need for hourly or even half hourly weather forecasting system becomes very crucial. And this advanced level, analytics is really important in terms of scheduling the generators and maintaining the grid stability. And obviously, once we have these systems, then we also need to change or upgrade our traditional fault protection system in the power system, where we have to deploy, digital relays and digital infrastructure to monitor and control the power system components in a digital way. So these are the components or issues associated with with the massive penetration of renewable energy, primarily wind and solar, into the power grid. And if we just see for the Pakistan power system, and as we already saw the massive intake of solar PV systems in the power grid, and how it is behaving now, and what are the challenges which we are facing right now, and how we plan to address this. We have here the intraday load profile of the whole country. If we just see just last year, this black curve. So this is a typical load profile of 24 hours. On x-axis, the hours, and on y-axis we have this megawatts quantum of the demand and how it was being supplied. So the black curve is basically in last year. It was, as we all know that February, March is peak production time for solar PV systems. So in just last March 2024, we do not have much of the renewable energy or solar PV systems deployed or up and running in the country. So during the early hours, we have around 13,000 megawatt peak demand, and then when the sun starts shining, we have the solar PV systems starting generation, and then during the mid of the day, around 11 or 12 a.m., 11 a.m. or 12 p.m. So we have the dip was around from 12,000 to only 10,000 megawatts. So it is not significant, and the generators in the system which are capable to ramp down or ramp up, primarily gas turbines and the hydro power plants, they were able to maintain the grid stability to ramp down. And then similarly, when the sun starts setting, and from 3 p.m., 4 p.m. onwards, the generation starts ramping up from conventional power plants. So this was not a big challenge a year ago. Just now, if we see this blue curve, this is from 2025. So and this is the first day of our Eid ul-Fitr, the national holiday as well, or a big religious festival. We have the peak demand of 14,000 megawatts in the country around 6 or 7 a.m. early in the morning. Then because of the massive PV system installed in the country at the distributed level, our energy demand or starting dipping from 14,000 megawatt to it came down to 6,000 megawatt. That is 8,000 megawatt of decline in a span of just 4 to 5 hours. This is because of massive production from the solar PV systems, and because of the localized generation, the generators in the national basket were reduced. Their output was reduced from 14,000 megawatts to 6,000 megawatts, and this huge quantum and huge decline at a very fast ramp down rate is very challenging for the system operator. And this does not on this not only resulted into a big problem or in terms of maintaining grid stability, but also over voltages and voltage issues and reverse power flows in the distribution networks. and which primarily translated into the transmission network as well. So again, once the solar sun started setting, then the demand started rising, and it went up to almost 12,000 megawatt at 8 p.m. So this decline and then ramp down and then ramp up every day is becoming more and more challenging for the system operator. So we just projected that if at the same pace the solar systems which have been imported in the country and they are being installed in the system, primarily in the low voltage and medium voltage networks, then this can be a more drastic curve. So starting from 15,000 megawatts early in the day, it can dip down to 2,000 megawatts. So this is a 12,000 megawatt of decrease within a span of 4 to 5 hours, and then again a rise of almost 8 to 10,000 megawatt within a span of 3 to 4 hours. So this sort of operation will definitely compromise the power system stability and may result in brownouts or blackouts in the whole country, which has huge economic impact. So going forward, we will see how we can manage this intermittency and how we can handle this issue in a more sustainable way. Just for as we already discussed and explained the need for grid modernization and upgradation so that we can keep moving forward with more renewable energy uptake in the system. So one of the options or technical solution is the use of high temperature low sag conductors. So high temperature low sag conductors, as we already know, can use the same right of way corridors, and obviously we just need to we will not need to install new transmission towers. The only thing we need to do is just change the hardware as well as the conductors on the existing transmission lines. So they almost supply enable you to carry almost double the power transfer of the existing transmission line without the need to construct a new transmission line. And obviously this is quick to deploy, and they can be operated high temperatures with very minimal sag. Primary reason for this is because they are not ACSR or aluminum conductor steel reinforced. They have a carbon fiber as a central core, which can be operated at high temperatures. So this enables them to carry more power to the load centers, or primarily if we talk about renewables, so we do not have to curtail the power. We can evacuate more power from the renewables by using these high temperature low sag conductors. So talking about some recent example or from our experience in power systems, so we have deployed almost 66.5 kilometer of 132 kV double circuit transmission line, which was on ACSR conductor, rail conductor, which we converted to HTLS conductor. So this is just a geographical layout of where we deployed this. This blue area is where we deployed this high voltage sag conductors, and obviously this area as well where so this project was completed in 3 years, and it's almost 8.2 million dollars. So this has a useful life of 30 years, so it can keep carrying supplying almost double the power requirements without using any new right-of-way corridor. Similarly, fax devices are an excellent solution to improve the grid stability, and with fax devices we can enable more VRE integration into the power grid. So this will enable increase the grid flexibility and reliability. So there are multiple fax devices available commercially, which includes static bar compensators or STATCOMs, and obviously transmission thyristor control, series compensation, and advanced power flow controllers. So now coupled with real-time dynamics and real-time control, these devices can act quickly and maintain voltage stability in the power grid by changing the reactive component of the electrical power. So we have one substation in Lahore region where there's a 220 132 kV substations where a static bar compensator has been deployed, and its size is for 50 MVR, so it can supply for 50 megawatt of reactive power instantly with a dynamic control system coupled with it, and it can absorb, in terms of all voltages, it can absorb 450 MVR to maintain voltage stability in the network. Battery energy storage systems at substations are the need of the hour right now, because they enhance the grid stability and flexibility to cater for more renewables. Primarily, the focus has been to accommodate more and more renewables into the distribution grid in the medium voltage and low voltage network. So battery energy storage system, once installed at multiple substations in the power network scattered all across the country, can help manage the peak load requirements, when we can use these battery energy storage systems to store energy during the hours of low demand. Primarily when we have more energy being generated from solar energy systems, we can use the conventional generators to install to store energy into the battery energy storage system installed in the network. So this will enable us to wheel the power from the power stations right at near the load centers. It will also help us to smooth the renewable energy being produced primarily in the wind power plants, or even from the rooftop solar system. So they can store surplus and intermittent nature of the renewable energy. And they also have the capability to, because of the advanced control systems attached with it and the PCS systems built into the battery energy storage systems, they can have a very good control on rear and reactive power management, whereby they can dynamically support or provide you the reactive power needed to maintain voltage stability. Obviously, they do have the capability to increase the voltage stability as well as the frequency stability. So the primary reserve as well as the requirements for all the variation in the power system. So these battery energy storage systems can act quickly and prevent the blackout or brownout from in the power system. And obviously, the ancillary services also fall into this category, where they can be used as primary reserves in the system, obviously to provide voltage stability and increase the reliability in the power system. And in terms of energy arbitrage, they can be an excellent source where they can use the power when it is very cheap in the system. They can use all this power to store inside the energy storage system, and then the same power can be supplied back to the grid when the demand rises, especially in the evening hours when we are, shifting back to the grid from the solar PV systems. So we have just one more example of battery energy storage system, which I can just share with you. So I guess you people can see my screen now. So we have one 132 kV substation where we have planned this battery energy storage system. So all the background, the issue as well as the challenge which we are facing, and how we plan to address this challenge by the use of battery energy storage system will be discussed in this couple of slides or moving forward. So we have this 132 kV substations, and this is primarily a residential area. This substation is supplying electricity to all the residential area in Lahore region. So this substation has been experiencing a lot of rooftop solar PV systems, and once we have more power flowing into the network, primarily from the rooftop to the low voltage and then to the high voltage system in the distribution network. So this substation has two number of power transformers, 2026 MVA, and against these in the downstream network in the 11 kV and 400 volt system, we have 41 or 42 megawatts of distributed generation installed, all in the rooftop of the households. So the substation has 52 MVA capacity, and almost 90% of the substation capacity we already have solar PV system deployed on the rooftops. And these systems are generating electricity during the day. So right now we can see we have 40 megawatts of solar PV system, and if all other houses in the same neighborhood in the residential area installed solar PV systems, then this can definitely has the potential of increasing from like 40 existing and 80 megawatt more. So it can jump to 120 megawatt if every other household in the vicinity installed a solar PV system at its rooftop. So this will definitely, be more than 200% of the installed capacity of the substations. So with just 40 megawatt installed in the system, we have been experiencing reverse power flows right from the rooftops to the substation during the day time once the solar PV systems are generating at its peak. So if we can see this curve, this is the cumulative curve of the whole substation. So we have at the in the early hours we have 5 megawatts, and then late in the night hours we have, when the sun is not available and all the power is supplied from the grid. So we have 20 megawatt being supplied to the load at the night hours. But during the day, we have this huge reverse power flow coming from the solar PV systems right to the substation, and then going forward to upstream into the transmission network. So reverse power flow is one of the challenges. The other big challenge is during the peak production of solar energy, we have massive over voltages. The normal criteria in the grid code is plus minus 5% of the standard value, but now we are facing more than 10%, almost 10% of over voltages above the standard limits. And also, as we have this inverter-based generation, and they are generating electricity at unity power factor, so or 0.95 power factor, or in the lagging state. So during the day hours, once we have massive solar PV generation, the power factor on the substation dips to 0.5, 0.6. So all the reactive power is being supplied from the grid, and the active power is generated from the rooftop PV systems, which is consumed from the loads connected to the PV systems. So all these challenges are becoming more and more critical with reverse power flows, with the over voltages and the power factor dips. So to address these challenges, we are facing right now a reverse power flow where our traditional power system has unidirectional power flow. So it is rather than having a passive network, it has become an active network where we have power flows in the morning coming back from the rooftop PV systems to the grid, and then at the night time the grid is supplying power to the household. So it is becoming more and more active now, which is creating protection challenges as well as thermal overloading of the existing equipment and our distribution transformers, which are primarily designed for unidirectional power flows. So all these are creating a lot of stress on the distribution system. So we have done planning for 132 kV battery energy storage system, which we plan to deploy at the 132 kV substation, and it will be interfaced at the medium voltage level of the 132 kV substation. So we have done 3 scenarios where the operation of the battery energy storage system has been evaluated in the grid forming mode. The other is peak shaving mode, and the third one is the best case scenario, the ideal scenario, where we have how much quantum of how much size of the battery energy storage system we need to to store all the surplus energy flowing back into the grid during the peak power generation hours. So if we just see grid forming mode, then we have this result from the simulation. Then we have this power flow curve, which we already see that during the day hours, this dips down to reverse, and all this power is basically, this energy is going back from the rooftop to the substation. So we can use we can install this battery at a substation and store this energy into the battery energy storage system during the day hour. And then, so this is a 10 megawatt hour battery energy storage system, and it can supply the same energy during these hours, and then this peak demand can be supplied from the battery energy storage system during the evening and night hours. Similarly, when we have peak shaving mode enabled for this battery energy storage system, then it will only store energy once it starts dipping below the reverse power flow, and then it will shave this peak and store all this energy in this area into the storage available at the substation, and then the same can be supplied back once from the evening hours from 7 p.m. till 24 night 12 p.m. time. So hereby we will have this revised peak curve. In an ideal scenario where we need around, we simulated that we need 28 megawatt hour of storage to flatten the curve. So this way we will have to store all this energy available in the system to in the battery energy storage system, and then supply it back to the grid. So this will obviously is a big number, and obviously it requires a lot of investment as well. So in terms of some high level design of the battery energy storage system, we have these just at the bottom we have the storage cells. So these are containerized solutions to be installed right at the substation switchyard. So these will have storage cells in them. And then upstream we have 11 kV or medium voltage network, where it will be interfaced into the medium voltage switchgear room of the substations with a step down transformer from 0.69 kV to 11 kV. So it can step up and step down at the same level. And then we have these 1.5 megawatt into 2 power conversion system, which can store energy at 3 megawatt per hour into these storage cells. And then similarly it can also supply back energy when needed at 3 megawatt per hour to the distribution grid. Similarly, it has an auxiliary transformer, a very small number, 10 kVA, which can be used to to cool the system, and then energy meters are there. And this all has a digital control which can be remotely controlled from the national power control centers with all internet connectivity, and when to charge and when to discharge this battery energy storage system. This is an overview of the containers design. So these are 40 feet containers. So 3 of them will be required. This is basically this container is basically having all the storage system in it. This has the power conversion system and also some storage, and this has complete storage system. So one of these containers can host around 4.5 megawatt hour of storage in it, and they can be stacked up as well depending upon the space requirements. If there is limited space, the 2 of them can be stacked on top of each other. So that's all from my side for this session. So we can just jump to some questions which we might have. So over to Asan from my side.
Thank you very much, Arkam, for a very detailed presentation, and very rightly mentioned technologies which are required at this moment for dealing with the stability and the reliability of the future electricity grids in SAARC region. So, Arkam, we have a quick question, rather a query from one of the participants. I would try to explain what you meant. he says that weather forecasting techniques are available. Do you, in your projects or in your company, use any of those techniques for planning a day ahead power generation and power load matching of these things? For example, advanced understanding of cloudy or sunny days, and do you have any AI or digital tools for that?
Yeah, so we are in touch with a couple of companies who provide AI-based, those who have developed some tools which use AI-based energy forecasting as well as primarily weather forecasts. So they can help us a lot in terms of scheduling the power output and also the unit commitment schedule. So one of these companies is very interesting, grid driven. So they have these power AI based tools, and the same can be used for to predict the output from wind and solar power plants, and also for scheduling as well as for transmission as well. So their solution is dynamic line rating based on AI based forecasting techniques. We have not started deploying it, but we are in discussions with them to use those.
We have been asked many times by the participants, just for the information of the participant, that all the presentations during this webinar shall be uploaded on our official website after the conclusion of the webinar. Plus, on top of that, we will also share the video recording on our YouTube channel. We will provide the links in our website. So anybody, if he misses anything, he can watch it later on. So another quick question from you, Arkham, before we go to the next presenter. You haven't spoken much, but you have spoken much about the battery storage and the other technologies. But what about the this pumped hydro storage technology? Are they feasible in catching up the small demand and small fluctuations?
Yeah, definitely. These are obviously the need of the hour. All these solution systems, as I already, I just touched it a little, that these can because these have been there in the history as well, and now their need is more and more important, and we definitely need to have those sort of pumped hydro storage system as well, and a lot of countries are looking into this as well. It all depends upon the territory and terrain and whether we can develop something like that. And obviously, the more important factor and the driving factor right now is the speed at which we can develop that. So pump storage sometimes is a bit tricky. Sometimes it takes a lot of time as well as the investment. On the other side, if we look at how batteries are behaving, so they are becoming more and more commercially viable in terms of their declining prices as well as their increased, life cycle. So they are quick to deploy. They are just plug and play, all containerized, and they can be ramped up so quickly. So I guess it's more of some practicality. Both offer the same solution, and technically they can manage the things, but obviously commercially, which is more viable and which is practically quickly to be done. So that remains to be looked into for a project to project or country to country basis.
Okay, thank you very much, Arkam. So for the information of participants, Mr. Arkam shall be available till the end of the webinar. So if you have any questions, you can still ask them and we will cater them after the conclusion of our second presenter's presentation. Thank you very much, Arkam. We'll see you later on.
Thank you. Thank you.
So now ladies and gentlemen, now we move on to our next presenter, who is an engineer, Mohammad Zakia, who completed his BSc Electrical Power from UT Tesla in 1999. He joined Islamabad Electric Supply Company and served there for 6 years, and then moved to National Power Control Center of National Transmission and Dispatch Company (NTDC) in 2006. He has served in various departments in NPCC, including Control Room LD, Section Corporation Planning, and remained part of CPBCM preparation. He moved from NTDC to Independent System and Market Operator ISMO Islamabad, where he is currently the Executive Director. With extensive experience in grid management and real-time system operations, he leads the strategic oversight of national power system reliability. His leadership is instrumental in ensuring secure, efficient, and transparent operations across Pakistan's evolving electricity landscape. So, do we have Zikriya Saab on board? Can you hear our voice, sir?
Yes, Khalid. Am I audible to all?
Yes, sir. You are audible. Can you share your slides and start the presentation?
Sure.
Sir, your slides are visible. Now, can you, if you wish, you can turn on your camera too, if you wish. Sir.
Sure. Camera on.
We have lost your slides. Can you share it again? We had a problem with the previous presenter also. Once you turn it on the full mode, then it just gets away. So this way it's okay. Slides.
I hope presentation is audible to all of you, viewed by all of you in
Yes,
full
sir.
presentation mode.
It's perfectly
Sure.
fine.
Bismillah ar-Rahman Thank you very much, SAARC, to invite me in such good venue and for presentation for great practices. This is need of the day as we are facing challenges. Our earlier presenter have presented and frame the issue in a detail. My presentation will focus on the actual what we are doing in with National Grid, being the system operator. My journey as have been introduced by Khalik Saab. That was my journey, and presently I'm working as executive director. So I will little bit start with the journey of National Power Control Center, and then we'll move on the actual case of the today. This will be the sequence of the presentation. Just a few words about the evolution of the system operator of Pakistan. So next, the new journey as we have started since May 2025, role of independent system and market operator. Then we'll show a slide of generation mix. Then we come to the actual case of today, renewable-based electrification. What is the need? Renewable energy landscape and Pakistan's change power demand landscape. The impact of renewable on Pakistan power's demand. Challenges due to increased VR integration with national grid, with the demand profile, with load scheduling, load dispatch scheduling. Next will be the grid practices, the actual practices, what should be adopted and what we have started in the real time to cope with these challenges. So some way forwarded and conclusion, then we'll be going to the question and answer session. This is a slide starting the load dispatch center history. Initially, it was called a load dispatch center. The journey started in 1917 from Kodlakpat, Lahore. That was a very small system. The first SCADA upgradation started from 1980s, and the National Power Control Center building in Islamabad inaugurated and started its function with SCADA upgradation, first upgradation ABB in 1991. Then we moved to the second upgradation of the SCADA due to the increase in our network and our generation addition and change of the technology. The project started 2010, and have been functional from I think 2013. That is called SCADA 2 project. Now we are in the process of upgradation of SCADA 3 project, having the scope of thousands of the sites access for integration. The need of the SCADA 3 became due to the increase of 2002 policy generation, network expansion, evolution of the system to cope with the increased demand challenges from 2013 to 2018. This is in process. 70% work has been completed, and our new control room have been started in NPCC building Islamabad. Then I will just introduce the independent system and market operator, what was the need to create and what the government is going on. So little about why independent system and market operator. Everyone in the world, system operator always become independent and neutral. Conflict of interest everywhere arises with if we are with TNO, if we are with any power purchase agency, or we are with any branch of regulator. So the need was impartiality, neutrality, and fairness. In our dispatch function, we should keep the fairness, being independent. If we will be independent, then we will be the fair. Biasness will not affect us. Conflict-free operation, as I already told, the dispatch, if any conflict arises, we will and we have the powers to resolve that conflict with our stakeholders. So transparency in the function, what we are doing should be published. They should be on our websites. Initially, we have only NTDC website. Limited information were there. Now, ISMO website have been started, and many of the informations are landed over the website, and the journey is continued. What functions we are doing, what dispatch is doing, what is the merit order, all things are transparently uploaded on our website. So these all things will definitely improve our credibility in our public, in our stakeholders, in the eyes of international investors, that Pakistan is doing a dispatch job, a conflict-free, neutral, impartiality in dispatch. So investors will gain the confidence. So what will be the role of independent system and market operator? Previously, we were the system operator of Pakistan. We have the only job of system operation. In serial number 2, that was generation dispatch, the available pool, economical dispatch, in what way, the network operation, the primary network operation, and obviously 500 kV transmission network, 220 kV transmission network, and we have the control of 132 kV transmission network of all discos from our regional control. Operational planning, commercial settlements, port dispatch settlements of the IPPs and generators, what payments have been made to them. All things have been verified and communicated to power purchaser from the system operator. Now the role has extended. Previously the planning role was with NGC, NTDC. Now the integrated system planning. Previously we called it the system planning. Now the ISP become the merger of long-term generation planning and long-term transmission planning. The long-term generation planning, we said IGCEP, the term Integrated Generation Capacity Expansion Plan, and TCEP, the Transmission Expansion Plan. First time of the history, ISMO has submitted with regulator the document ISP, together both generation planning and transmission expansion planning. Third function, long-term demand forecast. Obviously, demand forecast linked with the transmission planning, generation planning, and generation planning linked with the transmission planning. So system operator role, I already defined. The third major role, our journey towards the multiple buyer regime, that is market operation. Market operator was previously attached with the power purchaser CPPA. Now, as new, we have our own license of system operation with NTDC and market operation with CPPA. Now, these both licenses have been transferred to ISMO, and the new the entity can evolve from May 25. So the market operation, what they have to do, registration, participants, and contracts will start running IT platforms. We have started the readiness for CTBCM from 3 years back. From last 2 years, we are reporting marginal pricing to our regulator regularly. We have onboard all the IT platforms, all the softwares, the meeting service provider from NGC, and what things to run the CTBCM, all prerequisites have been completed. We are ready to launch the market. The wheeling regulations are on with the regulator. Other frameworks have been approved by the government, and soon, maybe end of this month or the first week of the October, the CMOD for market will be started and will be announced. The third function, settlement, and obviously when market will start, the settlements will be done by the market operator, designed for future evolution of competitive market. We have started with the bulk power consumer and suppliers initially, then will be the merchant based, then hope this should add value in our economy growth. We hope this should be success of this. Although all of you know that challenges are there, our tariff rate are high. We are dependent on the imported fuels and dollar-based imports. So that hits the well market, but obviously we have a journey towards the renewable, maybe renewable take part in a market. The last most important function will be the monitoring and compliance. In grid code, we have obligated that we will monitor our own and our stakeholders like TNOs, generators, and are associated with the dispatch function to whom we have to coordinate will be monitored as per grid code. This is just all of you know, being engineers and industry experts and system operators, the generation dispatch. The dispatch, we have the balance of demand and supply. But demand, to cater the demand, we have to the supply to dispatch the supply. Generation dispatch, short-term load forecast, unit commitment, and economic dispatch. Economic dispatch, all of you know that. But we are running within security constraint economic dispatch, the term. So in all the world, you know, constraints are everywhere in our system. So the dispatch, economic dispatch will move to the security constraint economic dispatch. Power system operation and control. This is network operation, safe, secure, and reliable system operation. This is again, when demand go down, generation will be excess. This slide shows that generation dispatch. Again, this is our function to balance this imbalance, to balance that is generation dispatch, system operation and dispatch. Again, when demand exceeds, supply down, again, the system operator function starts. This is the longitude. Our system is a longitudinal system. Our power system, the primary system I have shown in this slide. We have in the red lines all are the 500 kV transmission network. This purple color is, you know, HVDC 660 kV transmission from Atiyari to Lahore converter station started in 2021. We are using this line very efficiently, not up to the mark, but this is very became important for us because in previous winters we have faced 3 times the AC corridor splitting, and this DC transmission line save our network from south to north interlink. The stem remains stable due to this new evolution of the system. So we have 3 zones in our system: north zone, central zone, and south zone. In north zone, we have a capacity of hydro generation, a huge capacity available and in near future available, you know, Mangla, Tabela, other hydro projects, Nilam Jhelum, like other CPA projects. In pipelines, we have Dasu, Damir Basha, Mohammed Dam. All these projects are in north. In load center, we have fossil fuel plants, RNG-based plants, some solars, bagasse, and nuclear resources in our PESCO region. So these are generating resources are in the center, in these center areas. The CPAC projects are the cheapest in the thermal rating of the power generation that is in our south system. In southern, our big two nuclear plants in south of the region. Our wind corridor is in the south. And our local coal and imported coal all in the south. So this is again a big challenge for the system operator to travel this huge cheaper generation from one corner of the country to the load center or other corner of the country. Obviously, this HVDC line helps more and more, but there are another challenges to meet this export level in combination of HVAC and HVDC corridors, because we have not up to the mark HVAC link compared to meet the HVDC criteria. So we are in planning with certain technology improvements and addition of lines. Later on, I will discuss with in detail. So this is at present is a challenge for us to travel this cheaper generation from south to load center. So this is a brief. We have a national control center in Islamabad to cope with all generation control, dispatch, switching, and operation control. We have HVDC line, one HVAC, and including we have one tie line with K Electric. One another most important thing from start of the city BCM, KE will be centrally dispatched. KE generators also will be come into centrally dispatched to give the opportunity to all the stakeholders to participate in the market, city BCM or in the market regime. So to purpose to take the KE in central dispatches to a single marginal price. The dispatch will be central. KE generators will be dispatched from this control room as well. These 3 days we are in coordinating with the KE to get them their generators in our dispatch modules and control modules. So we have 2 regional control. As earlier I said that the 132 kV network of the whole system is also controlled around the NPCC. 2 regional controls, one is regional control north and another is regional control south. North deal with 132 kV northern network up to extreme of MEPCO, and the south deal with 2 HESCO discos, HESCO, SEPCO and KESCO, 3 discos and extreme level of MEPCO. This whole network, GB is not in our network and K is with our tie line. So what we are doing, this is a simple thing, year ahead planning. We are doing allocation of maintenance, non-maintenance months and demonstration pays as per PPA agreement. This is a system operator job. Year ahead energy targets to power producers, all generators. Quarter ahead, these are PP arrangements, week ahead, day ahead, and scheduling of the IPP. This is just a glimpse of the operational hierarchy of the system operator. So system operation planning, in what we do in operation planning, we do short-term load forecast. After integration of wind, the wind forecast became another topic for us, solar generation another topic for us. We have our own R&D department. Previously, we have engaged a consultant from abroad to forecast these wind generation for us. But unfortunately, due to limited access to the generators, they could not provide the as desired forecast. So we create 2 years back our own R&D department at NPCC. We coordinate with all the renewable generating resources, take their inputs for the forecast to our module, and at the moment our R&D is fully functional and we have displayed these wind generation forecast to our control room for their operations. Our accuracy level is as per the grid code under 10%. Some days we are in 3% band, we are in 5% band. We are compliant with the grid code. Solar energy, another is solar generation forecast. No, at moment only 3 solar plants forecasts have been displayed to the control room. The rest 3 are in process, and we are moving to the analysis of the rooftop and off-grid solarization that have been started since last 2 years in the country. So that figure will help us in our unit commitment, in our dispatch and scheduling. At present, we are planning with our daytime that duck curve values put in the model, but actual that figures are higher side. And currently PPMC, Power Planner and World Bank are jointly studying the rooftop solar figures of the load centers, MEPCO, LESCO, GAPCO and FESCO. These are very crucial for us for generation dispatch for daily basis. This slide just showing energy mix of the country. You are seeing that we have this previous installed capacity, but this capacity now reduced. We have the thermal plants have been retired. This all figures have the 2600 megawatt of the thermal retired. Some other IPPs have been retired, and now the capacity down to the 35,000. So we have the major 29% of our hydel, and wind is 5%. Maybe in future, in market-based wind will be increased. And solar, this is solar only, utility scale solars. We do not, in this capacity, the rooftop solar or PV solars. This is a small brief of network. We have one HVDC line, as earlier I said, that have 4,000 megawatt capacity and 886 kilometer of length. Another 500 kV grid system. We have 21 grid stations, 46 of transformers, 65 of transmission lines of 500 kV line, and this is the kilometer 8,484 of 500 primary transmission line length, a huge network of longitudinal in Pakistan. Rest 220, 11,000 kilometer. Power plants we have about 140, 145 total, including GENCOs, including our winds and solars, all including. These are our power generating resources. Only one system operator is dealing with all these power generation or such huge network of the country. So now we come to the today's topic, renewable-based electrification. First, we can discuss. We are facing being system operator, but we will another way add the value to inclusion of these renewables. What are the purposes in here? Climate change mitigations. We are facing with climate change as a use of fossil fuels, coal, and etc. So that impact our climate, especially in winter seasons. We are facing fog and smoke issues in some areas. So all these are climate change mitigations if we are introduce renewables as targeted by the government. Energy security and independence. Yes, energy security and independence means independence of that means import bills and import fuels. Economic benefits, again, if we have the renewables in our country that have no fuel using, we will have limited or we will withdraw with the import bills for importing the imported fuels. Excess electrification, yes, at remote areas, consumer can get these renewables by their own solar installations. If they are not connected with the grid, they use these renewables. Even then wind with the remote area they can use. Grid modernization, yes, for renewables, if we work with the grid will be modernized with the current practices. Demand growth and future proofing, yes, if demand grows and the renewable introduced in the system, that will cope with the increasing of demand irrespective of the grid challenges or another things, but demand will be, the gap will be made with this renewable inclusions irrespective of fossil fuels and other addition of the generation resources. So these figures from our submitted IGCEP indicative generation and expansion plan. The policy ambitious that government targets 60% of clean energy VREs, distributed energy resources in generation mix by 2030. Required major investment interventions in grid infrastructure. Obviously, we need, I will discuss in another coming slides, what have to do and what we are doing. So these are the figures. VRE, currently we are in 25, 30%, 30%. It will goes to 23%. Hydro well from 28 to 33%. Thermal, yes, that will be reduced. So renewable well definitely increased. The operation challenges, yes, balanced demand and supply integration, variable renewable energy, yes, that's another will be challenge. If renewables increase, the another challenge to us for national grid for their integration with the existing infrastructure. First, we have to build infrastructure, and then will we meet the target set fixed by the government and ensuring grid reliability. Yes, for renewables, grid reliability is important because only a line outage will impact the whole. In all other network operation, a line outage not a problem with the system operator, but the line connected with any energy resource, especially with the VRE, renewable, that sudden disconnect the VRE generation with the load center, and that impact our generation scheduling and operation in control room. So in verifications, we are solar PV and the renewables. The hydro include CASA 1000 also have been included. We are hoping that this project will be succeed, but currently this is in very lagging form. This is a glimpse picture of our that IGSEP figures that where we are in wind. We can see in 25. This is the quantum. This wind will go in these figures in 2030. These will yes meet if our demand grow as per our IGSEP, as per the demand growth figures given by the Planning Commission to us for 10 years horizon. PV solar, you see here, at current, I already told that we have get this figure from our duck curve, from our daily load variation of the daytime, what figures we see. So these will be go to the 9,000. The huge increase in these PV solars. Other hydro, yes, hydro will increase this 16,000 or about 17,000. And at the moment we have just add 9,000 hydro, it goes to the 70,000. So huge increase to meet future demand clearly indicate that we are based on these renewables. So this is PV solar inclusion. We shown that from the journey starts from 2021. As earlier speaker also mentioned, the journey in figures. So these small figures, small addition shows. And when we goes to 2022, this is again shows the daytime solar little addition of pattern, this generation pattern. When we go to 2023, yes, this pattern shows some solarization. And we go to 2024, again this curve start this from 7 hours to this to noon, its peak. This shows some solar addition in the system. So when we go to the 2025, the year of 24-25, that was again all known that the import of solar panels and solar PV solar installation and net metering, when the installation authority shift from regulator to the distribution companies. So at distribution level, huge intervention have been made. Consumer install more capacity than their demand. The another challenge for that the consumer having load of 3 kilowatt of the house, he installed 15 kilowatt of the system. So most of the daytime he exported to the grid. You can say this curve, the huge decline in the daytime and in this dark curve. So this is a challenge for a system operator to keep with this change and with then rise and the peak you say above the normal range. Our load profile shift from day pattern to peak and night hours. Our peak recorded peaks are on mid of the night, 24 hours, 11 hours, 11 p.m. So these are the hours when we recorded our maximum peak of the system and whole day. What we are doing, we are committing the expensive plants in the night hours and peak hours. This is challenge for system operator. So this is the journey of solar. You can see from these illustrations, and the coming year further challenges for us. So in as earlier presenter concerned that During special days, we face is major challenge. Like in Eid al-Fitr in this year, in 2025, when I was in control room during the Eid day, you imagine our country load demand comes down to 6,000 megawatt and to maybe 5,800 megawatt. We maintain our system with a single 500 kV transmission link due to the over voltages. What happened? All consumers having the rooftop solar installed in their roofs. That was the clean day. Solar was in high penetration. Houses and industries, houses empty, industries off. They all export the solar generation to the grid. Imagine when I talk with the CEO Lesco, he astonished that, sir, my grid is negative. At that time, at that scenario, 30th of the March, the LESCO demand as historian maybe 2200, 2400. At that time, LESCO was drawing only 600 from the grid. That was with only one disco. So the whole system become down to the 6,000 megawatt, and that was we have to do with some intervention that cannot be speak here to free uplift of power, where the load management, policy load management has been carried out in the country, where recovery and losses are higher figures. So at that day, we cope the system maintain with that strategy, because we cannot stop the solar addition export to the grid. This the duck curve, this the gap. I already told that we are copying these figures from this curve, the figures we are used in our planning section. So this is the again journey 2021. This was start, and in 2025 you can see how rapidly it increased and what will be with us with the next year. We cannot imagine. So this is challenges for a system operator. If any audience from the system operator, they can betterly know what system operator have to meet all these challenges in such scenarios when they have no such modernizations in practice at the moment. Yes, we are doing with that, but it will take at least 1.5 and 2 years. So challenges due to increased VR integration, what challenges are? We have the frequency regulations. Intermittency is the big challenge, and the forecasting error. If forecasting error increases, we were lagging with the scheduling and dispatching earlier for day ahead dispatching. And intermittency, yes, how it if we come to the solar park, if a cloud comes suddenly, so sudden drop of the generation of 500 or 600 megawatt, if we have the fast frequency reserve, we can meet with that situation. Large units contingencies we have in the grid. K2 and K3 1040 megawatt each have the largest units, and we put the reserve policy with the regulator having 1000 megawatt to allow us in the system to keep as reserves. So these are our reserve contingencies. Consumers become prosumers. Net meter plus rooftop, off-grid solar plus batteries. These are increased VRE integrations. VRE generation curtailment risk. Yes, VRE increased. So curtailment due to two factors. One is demand decline. At present days, our demand is declined in such a manner, such a way. During 11 hours, during 12 hours, we are at maximum low level of the demand of the September in history of September. So what we are doing, we are controlling frequency by curtailment of the generation resources, including VREs, as these are must run bus, but we have no choice to take meet with this demand defection issue. Another is if any network issue at the where VRE is connected, that are the second scenarios became. Initially, they are first scenarios of network availability, the possibility. No, the network is available. The curtailment is on demand side management. Yes, duck curve again. high daytime solar output, and steep evening ramps. So the ramps, another challenge with our generators. What we are doing, we are ramped down all the generators with their minimum level, and most of them to shut down. We have no ramp down quantum in high water season. This is the peak water season, and hydel generation it's a peak. So no regulation at hydel site available. So what we are doing, we are keep off the generators, and then evening time we have to start again. There is combined cycle or other generators. That is an issue. We have taken total of their start and stop available starts in the year of their generators. That is another. Sharp load variation, as already said, wind speed, that forecast we are doing, but our climate changes are, as you all know, that sudden sharp variation in wind speeds and in clouds. Sudden clouds came and the load will drop, and a wind, high wind in or wind off. Our 2023 blackout was also somehow linked with the renewable, that is the wind forecast. That was the wind came more than their forecast. Curtailment and stability risk, yes, stability risk again, high voltages on the over the system, because we have already said 7,000 kilometer transmission network in low demand scenarios. When we are at low demand times, the network generates its reactive power and the high voltage itself. I am talking about the primary network of the system. At distribution level, yes, DISCOs also facing in reverse power flow and their network overloading our voltages on their 11 kV and their transformer and 132 kV issues. But these come up as a whole, come to the primary transmission network. Grid resilience and black start capabilities. Yes, black start, as wind do not give us black start, solar installation will not give us black start. We have to move to the other options. These are the challenges. So what grid practices for renewable electrification? Application of modern forecasting tools, as earlier said, this forecasting for demand forecast and renewable forecast. Both are important for a grid operator. So we are doing with our R&D department in NPCC ISM office renewable forecast, and we are moving to DISCO-wise forecast and our R&D level. The alternate is in our SCADA 3 project, rebasing tools, inbuilt tools. We are working with them for better demand side forecast, system demand. In that application, the EMS, GMS application will allow us the renewable forecast as well demand forecast. So after operations of SCADA 3 fully, we will be in a better position to meet with these forecasting issues. Storage technology, yes, already told by earlier presenter, this BESS is the only we have, rather than pumping storage, we have the best. We are doing with a pilot project in JMP 20 or 25 megawatt BESS capacity. That is 70% work has been completed. The another 500 megawatt I will show in next slide, a BESS, and incremental increase with IGCEP forecast. The BESS we have issue a study and need based. Now ADB is funding that project. That is initially forecast at GMP. So smart grid applications, SCADA, yes, I already told that SCADA is on SCADA 3, the upgraded version, Hitachi based. SCADA is now in process, 70% work has been completed. Our control room and backup control room both have been operationalized. Another WAMPAC, yes, previously wide area monitoring management techniques, not in our grid, in Pakistan grid. First time we lesson learned from last hour blackouts, brownouts. We feel that in our system, in some locations, some critical locations, we should have the WAMs. So the study has been completed airbag. 5 locations, 6 locations have been identified. The RFP and other things have been done. Now we are in bidding phase to install these VAMs all. So by end of next year, we inshallah will be available with these 5 location VAMs. These VAMs will help us to identify any oscillation in the system earlier than any SCADA intimation. So SCADA with a delay. So VAMs are VAM, and then we will move. Initial project is VAM, and then we will move with the complete solution VAM pack. So if VAM will in place, the VAM pack will be the easy solution to add the control and other automation to damp down the oscillations created from any part. Energy management storage, yes, already base is working on this. AMR meter in AMRs in our distribution side, there's already discos are working on this. These are the techniques of the smart grid, and these are all in place in parallel working, and inshallah hopefully we will be in a better position after 1.5 years. Dynamic reactive power compensations, yes, these are the need of the day. So STATCOMs and SVCs. We have conducted a study with Jay-Z, Italian company, for grid modernization of NTDC and grid system challenges. So that study has been completed. We have initially finalized 5 locations for installation of STATCOMs. So now we are working closely with the consultant of World Bank to further mature these STATCOMs installation with future demands as forecast in the IGSEP. And further SVCs, yes, and serious compensations also beneficially for long length lines for power flow. Early study shows that these compensations will improve our transfer capability from south to north. At least 500 to 1000 megawatt will increase. So the second phase has been started, and we are including the rooftop solar quantum already exists in the country. That will give the result after mid of October. Then that will be included in a study, and that will help in Lahore side voltages in the load center. After that, we are in a position to make the PC1. Funding has been secured for STATCOMs and SVCs. And another, we are also working with our retired plants. I could do sink condensers. Sink condensers is better option, and world is working on sink condensers. So we also done a study for use of sink condenser from Guddu and Muzaffargarh area. STATCOM and sink condenser parallel studies are in place. So after completion of the study, we will decide what options. In some places we are beneficial with STATCOMs, and in some places we are beneficially with sink condensers, and in 2 or 3 locations we are very much comfortable with series compensations. For all these, we should have an ancillary services market mechanism. Yes, if based in our system, STATCOMs, SVCs, so we should have an ancillary services market mechanism. Flexibilization of the conventional generators. Yes, the conventional generators should be flexible to give us the ramp rates. Enabling policy and regulatory frameworks are needed. Some are in place in your Grid Code 2023, and some we should to add when such these evolutions came in place, when best STATCOMs are in place. So what will need of the time? Strengthening and modernization the transmission and distribution network. Yes, our earlier already the presenter shows that this will play a major role in our transfer capacities, our network reliability, voltage controls, if we work on our transmission and distribution grid both in parallel. Because distribution work is the most important. If the distribution is strengthened, the distribution grid will help in 132 kV level, and 132 kV level will help to the primary transmission network and obviously to the system operator. DRs realize distributed energy resources management, monitoring and integration. So rooftop solars and other resources, these should be monitored and integrated properly. At the moment, we have no mechanism. Consumer goes to the any office of the subdivision of the operation subdivision and get a connection. We have no any monitoring. We have no any figures and counting of that at what level we have installed capacity of net meter or off-grid solar, and the scatter there where there is no link with the grid. So all should be that also impact our future demand growth. If a consumer have scattered their own resources, that is disconnect. Initially, we have made as per commission figures that growth we include in our planning. That will increase our demand, but consumer do not connect with the grid, and he choice to be that solution, that distributed solution. So that will also our improved, what figures we have counted in IGSEP, they will impact. Application of modern forecasting tools, all are well aware. We have just in less than this accurate scheduling. The scheduling that they had the operator do for one day before for the next day. What generated resources are available with me? What is the demand of discos have been distributed to me? What are renewables with me for the next day? This is accurate scheduling will help the better management. Reserve optimizations. So what reserves was spinning, lowering the spinning reserves. What reserves we decide to keep on bar and keep off bar spinning and cold reserve to focus on our cost. Reduce curtailments. Yes, the better management, the better technology used, the better visibility, the better storage system will reduce that curtailment. That will help the operator and to discourage the cheaper renewable energy resources curtailment. Grid stability, yes, of course, in all these actions will improve the grid stability. Short-term forecast help manage grid ramping of solar, wind, and maintain frequency voltage. If you have better forecast from the tools, from the historian, our decision will remain stable the grid. Market participations, yes, enable VRE generators to commit energy reliability in electricity markets. We have a marginal pricing mechanism, a fair marginal pricing shown here in our websites to increase the confidence of the investors. So these are the important things. Advanced analytics, AI, as earlier speaker said, ML models and satellite weather data improve prediction of certain changes. Storage technologies, BESS. Yes, we have initially the study, the only two slides I have shown here, the study we have conducted. Yes, you can see here that this is the winter of peak season and the frequency it dropped from 49.04. If we have a 500 megawatt BESS system, so it will improve the frequency from 49.4. That is our grid code allows us from 49.04 to 49.4. This study we have submitted with ADB and working is in progress. So this is a winter of peak, and it is extra VRE in our system, fast frequency reserve if a BESS is available. So again, if frequency goes 48.8, it depends from the ROCA, what is the rate of change of frequency. Yes, in high demand season, rate of change of frequencies lower. So this 48.8 will come with 49.4 with this 500 megawatt addition. So these are our best studies we have conducted at ISMO in our own level and submitted to ADB.
Mr. Zikria, I can just
Yes.
Can you finish it in 5 to 6 minutes? We would like to give some time for the questions.
Okay, I will go on fast. Just a few slides, I think. So this is already linked with the ramp rate required. Slide shows that here the ramp rates we have available. These ramp rate capability with generators and load ramp rates are in decline. We have available these ramp rates, and when we go further in 2028, so available generator ramp rate will decline, and we will focus on ramp rate with the renewables to their best will or other storage system will help us. This is ramp rate. This slide actually shows us that available ramp and the in future ramp rates. So this slide shows the requirement of from 2027 we required the best with increased capacity, and with K2 K3 we are linked in the IGSEP figures 750 megawatt hour we will need the best system in our system. this is another solar system in the system. So we have to need these ramp rates. Currently this, and we need at that time when solar in the system, this solar shows in the net generation. This is the net generation in 35, it goes in 2034. So this ramp rate 71 megawatt per minute ramp rate will need us. Smart grids, SCADA, VAMs, VAMPEX, I already told about the benefits and what we are doing with it. We have application FACT devices. Already I told that the earlier presenter already told, and already these in SCADA and other FACT devices, STATCOM, SVCs. What will be they give us? Dynamic voltage support, reactive power support, low voltage, LVRT of renewable plants, power transfer capacity, improved from transient and small signal stability. Yes, we damp down the oscillations by using our WAMPEX, mitigation, harmonics, and oscillations. We all are the benefits of these FACT devices. Ancillary service market, we have required this market for frequency stability, reserve margins, for voltage support, and reserve and balancing of the market. For these three indicators, we should have an ancillary services market in place. Yes, flexibility compensations, reduced curtailments, and fair cost allocations. This fair cost allocation means the marginal price in market, which generator will be become the marginal price generator in the market. They should be fairly forecasted and will be published. Yes, flexibility of the convention generator already told that VRE generation support daily cycles, absorb variabilities. These are the benefits of the smart grid applications. Yes, management, monitoring, and integration are the future integration. Way forward, accelerate investment in the modern grid infrastructure. Yes, we should have the acceleration. We are already doing, but further acceleration we need. Yes, a scale up battery storage. We are further started at 500 megawatt in any other location of the load center or somewhere, in addition to existing 500 megawatt. Yes, strengthening regulatory framework is need of the day. Promote distributed energy resources, VPPs, and microgrids. Conclusion, renewable-based electrification is key to sustainable energy transition. Modern grid practices ensure flexibility, reliability, and resilience. Coordinating policies, market, and technologies is essential to run all these things. The future grid will be smarter, cleaner, and more decentralized. Yes, I go with speed, and this is the end of my presentation. I mostly focus on my own application, what the system order of Pakistan is doing with collaboration. It's a stakeholder rather than a generic presentation of the renewables. Thank you. Any questions related to this?
Thank you very much, Mr. Zikriya, for an excellent presentation. And you have rightly mentioned all the case of Pakistan's evolution and also mentioned about the NPC role and technologies and the projects which have been undertaken by the NPCs currently. Thank you very much. And to address the question, we would like our speakers, both Zikriya Saab and Mr. Arkim, to be very brief in your response. We have quite a number of questions from our participants. So first question is from Nabil Rahman. His question is that, do we have hosting capacity analysis for PV capacity in our current grid systems to control the system losses?
I think we do not have such capacity at present. At utility scale, yes, we are doing a small scale base in Jampir. I think in distributed level, Mr. Akam can answer that the battery system that come in, the distributed batteries will solve this issue. But I think still this is in question.
So, Arkam, would you like to respond on that one?
Yeah, definitely. So we do not have any, such analysis available right now, but we are in the process. All the utilities distribution companies are conducting such analysis to have the hosting capacity for their distribution grid in medium voltage and low voltage networks.
Okay. So another question is from Mr. Rinzin. He's from Bhutan. His question is that if the grid is not available for supply of energy from solar power plant, how it is compensated the generator and penalize the utility?
Yes, if a utility scale power plant is unable, we meet it with any fast ramping generator combined cycle. If we have hydro, we meet with hydro. If we hydro is not to give up us the regulation, we meet it with the fast ramp, the combined cycle. We have in low center sufficient fast ramping at moment combined cycle power plants. We meet from them, and yes. The AGC in SCADA 3 project, we have the application. Previously, we have the AGC only in hydel plants, 2 or 3 units. But in our upcoming project, we have 44 plants, and we are committed to activate automatic generation control in 25 plants, including hydel and fast track thermal plants that will help. And we are also working with them with the grid code compliance. The initial reserve, frequency reserve from group setting, that process SOPs are already on way. Currently, we are coping that with the hydel or fast ramp rate combined cycle plants. Yes.
So, Mr. Arkham, you may respond on this question. That if the distributed, it is basically from the perspective of distributed generation. So, if any household has a solar power plant at its rooftop, but the grid is not available, if there is some blackout of the grid, so obviously it is not able to transport it back to the grid and export the electricity and send it to the grid. So, does it put some penalty on the grid? Is there any regulation in Pakistan on that one?
Yeah, so right now there is no such regulation. Actually, the policy under which the rooftop solar are being installed, that clearly says that the primary purpose of installing such system is self-consumption, and any surplus, which because they are grid connected, grid tied inverters. So they will only work when the grid is available. When the grid is not available, they will not work. So it is net metering regime where you supply surplus energy in the day and then take it back. The purpose is to support the consumers from the grid side. The purpose is not to get compensation from the grid.
Okay. So, question from Mr. Zikria: how can ISMO ensure visibility of behind the meter and off-grid solar to improve dispatch and forecasting accuracy?
Yes, very good question from you. We are facing this issue. At present, there is no mechanism to have a visibility with all that figures. We take up this issue with PPMC, with the ministry, to take us that if any, because at a distribution level, there is no SCADA system. If we have central level, we have SCADA, but at distribution level, there is no SCADA system. Yes, how can we get visibility from that? That should, as previously you said, done an AMR system, a load demand and allocation and draw from the distribution level, that access is visible to the control room. If such a type can be done by the discos, and centrally the PITC department can do this to get that figures, that meters data, the at AMR. Yes, AMR can be linked automatically. That AMR data should be linked with the PITC and visibility can be gained.
Okay. So, thank you. Another question is: what capacity of a solar power plant is mandated to do forecasting to participate in the market?
I think presently there is no such figures have been identified for the market. Market is open. If we started, then we will seek that.
Okay. So we have a question from Mr. Athar. How can the hybridization of renewables with storage be integrated into grid codes and dispatch practices? Anybody can respond. Maybe Arkham can say a few words on this one.
Yeah, for this, I guess right now the distribution code is also being updated, in line with the grid code. So in context of that, so the primary objective is all the dispatchable generators start from 132 kV. So below that is embedded generators. So that has to be updated in terms of to have more flexibility and more control from the system operator perspective for the storage systems being installed at medium voltage level.
Okay. So we come up to last 1-2 questions. So we have a question that what are the economic implications for deploying these modern technologies in the grid?
Yeah, so basically, obviously, that's a very good question, and these technologies are not cheap. These are expensive. So, but there are ways where the world is looking into by creating a win-win where the private sector can be engaged, and they solve a problem for the power sector, for the national grid, and they take the revenue out of the challenges which they are saving. Like just for example, the battery energy storage system, the benefit they can give in terms of reduced marginal prices as well as peak shaving, that can be split up between the investor as well as the government side or the power sector, so that it creates a win-win and a sustainable way. That's a very good way of doing it. Otherwise, if we just keep on adding by from the private sector more investments and long-term PPA, then that will definitely increase the cost for end users which are connected to the grid.
So thank you very much, Arkam. And if Zakaria Saab, you want to say a few words, or should we go on? Okay. So now we come up to the conclusion of our webinar, and I'm extremely sorry to the participants. We have few more questions, but since we have already the time for our webinar is over, so what we will do is that we can address these questions. If you can put it up to us through email, we'll ask the participants or experts and then get back to you with the response. So I will now like to conclude our webinar. Thank you everyone for attending today's webinar. We have listened to excellent presentations delivered by the experts, Engineer Zakaria and Arkam Ilyas. Both presentations shall be available on the SCC's official website for downloading. Plus, the video recording of this whole webinar session will be available on our website. So if anybody wants to download and go through the webinar recording again, we can do so. And we would welcome any suggestions or any topics which are recommended by you for our future webinars. We would address them in our future webinars, and we would gladly do that. So with this, we are signing out. Thank you again for joining us today, and we look forward to seeing you again. Thank you very much, Zakaria. Thank you very much, Arkam, for your excellent presentation.
Thank you, sir. Thank you very much.